So we're going to start up again. We're talking about using an LTE network. We've got about, it looks like, what, about an hour and we got about an hour left. So I'm going to really blow through these next slides really fast to kind of get to the RF design part. So I apologize for that, but you have the information on the slides, and if you have questions, please, you can forward them to Kim, and we can try to get, if we don't answer it here, we'll try to get you an answer a bit later. And I'll be sending a copy of the slides to everyone after. Right. Yeah. So what on slides 79 and 81, I actually made a mistake and I reversed the figures on those. So there's going to be some corrections. So I'm going to send an updated PDF to Kim, and then she'll forward it out to everyone the next day or so, something like that. Let's see. Do we have the still in there? Oh, let's see. For some reason it's not going forward. Is it in It's in presentation mode, right? Yeah. Okay. Would you mind advancing the slides for me? Sorry. Next slide, please. Okay, so I'm just going to go through these real quick. So obviously there's going to be user equipment. The point here is there's not a whole lot of band class 14 devices out there now. One of the big issues is obviously going to be getting band class 14 chipsets into multiple UEs, various UE smartphones, tablets, laptops, the type of devices public safety uses now and will want to use in the future. I've just put some examples up here. Again, I don't endorse or favor any vendors over another. These are just some of the ones that I have seen. The one on the top right, the Max phone, we talked a little bit about LMR and LTE integration. That's a sleeve that a P25 sleeve that goes on an Android smartphone, which is one of the nice devices that could create sort of moving forward to some LMR LTE integration. But the devices don't end here. I mean, there's going to be a lot of machine-to-machine communications coming. Eventually, we'd like to see band class 14 chipsets in drones, beacons, and any IP-enabled device that can collect data for public safety or help public safety do their job. Drones, robots that might go into a building that's been demolished to look for survivors, that sort of thing, with all the video capabilities that you would sort of expect. Let's see. Just getting the presentation back up. Okay. Next slide, please. So this is not any kind of exact mapping of all the applications that public safety will be using, but this is just kind of an example. Verizon had a really nice quote they had in April 2013 that, at the time, about 50% of their wireless traffic was video. By 2017, they figured 2/3 of the traffic on their network would be video. So everything's moving towards video. The key point to put across here is that when you go into the upper right and you start doing interactive real-time HD video, obviously gaming's not something the public safety is probably going to be interested in, or whether it's a user or a robot using this video, it's very high throughput demands, and you start getting into very and you can also have potentially very latency sensitive issues as well. Motorola did a nice study. I put the source here where they tried to figure out what's the minimum throughput that one user would need at the cell edge to do video, and they came up with about 1 meg. You'll see much more values in that source. HD video on a user device with a screen size 3 to 9 inches that they could actually see and actually make use of. So that's kind of a good data point. Obviously, Colorado will be collecting their own user device information from their stakeholders to try to figure out what that minimum throughput needs to be in different counties, different tribes, different areas of operation. One of the issues that you also run into is you can do video compression techniques to try to compress video, especially on the uplink, because if you have very high capacity demands on the uplink in terms of throughput, you're going to need a lot of sites, and it gets very expensive. Any way that you can compress the video that's being recorded by public safety before putting it back on an uplink can potentially save a lot of throughput and save a lot of CapEx costs in the network. But when I mention this, some of the law enforcement personnel will tell me, well, if you start slowing video down or you compress it, in some cases, that might be considered altering the video, and then it may or not be admissible in court. I don't know if there's any law enforcement here in Colorado that has an opinion on that, or if that's an issue or not. But it's just something to think about, that, you know, it's a nice thing that the LTE RF engineers would like to do to compress video, but if it's something that starts affecting its usefulness in terms of data, which, you know, may need to be admissible in a court of law, maybe that's not even something that can be done. So next slide. Sorry. Oh, okay. Oh, good. Okay, we're good. We've got so one of the big key issues that Jason was talking about was right now public safety. If they have an enterprise contract for data with one of the carriers, when congestion happens at a cell site, they've got to compete with other users for those resources. I've worked a lot on WPS, wireless priority service, on CDMA networks, and also moving that onto LTE networks. There's a lot of quality of service, priority preemption mechanisms in LTE to take advantage of. I'm probably not going to go through each of these individually because it's going to take a bit of time, and I want to go through these slides. But in terms of just accessing the network on the over-the-air interface, are you allowed to access the network? We have something called an access class barring. That's been around in GSM. It's a little different in UMTS and LTE. It's basically an access class that is on your phone, and if you have an access class of 10 to 4, well, we would be looking at access class 12 to 14 for public safety and for security services and utilities. You could be exempt from a base station. If the base station will be, the eNode B will be getting a lot of congestion and utilization on its control channel, and it'll pass some threshold, could be 65, 75%, and it'll say, I'm going to go into overload. I can't have this many requests coming on the what they call the physical random access channel, the PRACH, coming at me from all these UEs. I've got to start throttling people back. And so what it does is it broadcasts out a value to all the UEs in its coverage area, and it can be per sector, per site, of basically saying, you cannot probe the network. You cannot try to talk to me until you do a self-calculation in the handset to beat this number that I'm broadcasting out to you. And in LTE, you've got to get under the number. In CDMA, you've got to get over the number. But it's a way of exempt. But if you have an access class that is exempt, in other words, an access class that's not 0 to 9, then you're exempt from that whole process, and you can start to probe for access to the over-the-air interface and the control channels to talk to the network to ask for something. Now, once you get through that phase, you can use an establishment clause, which will give you priority at the eNode B for messaging to the MME and the HSS, which is where your subscriber information is held, to get your credentials or who you are, get you identified to the network much more quickly. So access class barring to get through the over-the-air interface, establishment clause to speed up the process by which the eNode B needs to know who you are so it knows how to treat you. The next I'll talk about is actually the bullet on the bottom, is allocation and retention priority. These are values 1 to 15, with 1 being the highest. And you also have a preemption vulnerability. So you have a value that allows you to take a bearer away from someone else, and whether you can be preempted and have your bearer taken away. So you can imagine if there's a lot of congestion at the site and all the bearers are already taken by the public, if you've got a band class 14 site that you're leasing excess capacity off to the public and they've got data bearers set up, you can come in and you can rip that data bearer off, which we call preemption, and then you can steal that data bearer. And that's what you need to set up from which I showed down here at the bottom of the slide, from the UE to the packet gateway to actually do something with the network. You also have a preemption capability that determines whether you can be preempted or not. So once you've got that bearer, you'll be in a situation where no one else can preempt you. Now, the QoS class identifier is used at the nodes in the network, like the eNode B, serving gateway, packet gateway. Based on what type of application you're doing and what kind of bearer you have, how does it prioritize forwarding your packets through the network, upstream into the network to the packet gateway, and potentially outside of the LTE network to the internet or other packet data networks. And it uses diff-serve code points and assigns values that it can talk to other networks to give you priority for your packets within the LTE RAN and EPC, and also to external networks. So I'm going through this fast, but there's plenty of documentation. one thing I want to make a point of is last September, 3GPP actually started putting in new QCI values for mission critical point to talk and for signaling. Okay, provisioning and security. Obviously, when you have a network like that, you're going to have to provision users. You're going to have to manage devices. You're going to have an ability to remotely wipe devices. You're going to have to manage the applications on those devices. You're going to have to manage user priority during a public safety event. So these priority values that we talk about that sit in the core network, you could have static values, but you also want the ability to dynamically change them. So if there's like a chemical spill at an intersection and the police have higher priority values than hazmat crew, you may want to temporarily change that via the local PSAP, having local control into the core network just for that incident and change it back. So the point is that the technology is here to do a lot of QoS mechanisms. The real hard part is coming up with the agreements between the users with, and I'm sure PSAC is going to be heavily involved in this, who gets what level under what circumstance using what application. If the technology is there to do it, it's really the policy that's the hard part to sort out and the use cases. So security, because public safety uses VPN and they can be having access to public personal identifiable information, there's a lot of information that they have that hackers would like to have. It's very important to be able to authenticate users properly and to keep the integrity and confidentiality of that data. There's a lot in LTE. They're using 128-bit AES, but they're moving towards 256. There's a lot of stuff that's been written in standards about that. There are a lot of secret keys that are used between the USIM and the HSS, but they don't ever pass those keys on the over-the-air interface. There's a lot of intermediate keys that are calculated to keep those primary keys safe. A couple other points about security. Authentication and lawful intercept monitoring for UEs is still an issue. Jason was mentioning about fallback direct mode and proximity services. So when you have when the public safety functionality starts coming, it's in a lot of the 3GPP standards, but it's not going to be commercialized for a while. When you have the ability to go off network and have UEs talk directly to each other, there's an issue of lawful intercept and monitoring. How do you do that when a device is basically off the network for a period of time? We lose the... Okay. A couple other issues are public safety is has to use VPN a lot. There's a lot of commercial LTE networks where there may be a conflict between IPv6 and IPv4 because you don't have enough public addresses. Getting IP addresses assigned could potentially be an issue, especially if you're trying to do IPv4 mobile VPN over LTE networks, but the LTE carrier is giving out IPv6 addresses. And also VPN, use of VPN is going to have an impact on network performance and potentially on call prioritization. So 3GPP and other groups are looking at a lot of these issues. I'm really putting up there just for things to think about. Each of these bullets here could be topics onto their own for a workshop. Managing the network, I talked about local control already. Managing user equipment, keeping a list of approved, what are approved UEs, because you're going to have to make sure that the user experience is going to be somewhat similar across multiple UEs. How do you manage that? Who are the points of contact that are going to be providing those UEs? How are public safetyers going to get UEs? Who has a say in terms of what UEs are going to get band class 14 chipsets in them? We run into this in wireless priority service a lot because we do access control and CDMA now, and we'll be doing access class barring and LTE. Is some older handsets that are out there don't always take an over-the-air provisioning of the access class. So there's a lot of devices that public safety may want to use, need to make sure that all of these mechanisms, that these devices are up to speed with the standards, that they can use all these mechanisms and that you can over-the-air provision them, and that you're getting the functionality in the UEs that public safety wants to use. There's a lot of network management and operational considerations with this, asset manage. How are you going to develop test procedures to actually test a lot of the KPIs, the RAN and EPC metrics? that you've designed the network for to make sure that you're getting them on your network, that any infrastructure and spectrum sharing commercial partner is meeting those. A big point of that's going to be UE-based metrics collection. There's software out there, radio IP, NetMotion, InMotion, there's others, but you really only know the quality of the network if you're collecting metrics at the UE. Relying on OM peg counts and that sort of thing at the E node B won't tell you situations where someone couldn't access the E node B that wanted to. Okay, I'm going to blow through these two. I think I'll just let you read them. These are some of the functionality that's coming into the free GPP standards for public safety. We talked a little bit about release 11, a higher power UE when we were talking about, especially with boomer sites. Release 12, which was, I guess, the correct term, functionally froze in December 2014. Proximity services and direct communication mode was entering into the standards. The group communication service enablers supporting voice, video, and other data communications. We've talked about this public safety grade PTT. There's a lot of recommendations that NIPSTIC has provided. I'm not sure what the current discussion is on the group communication service enablers and LTE and how that might affect the network architecture, what's going to be part of the network, what's going to be an application interface on the UE. A lot of vendors are looking at EMBMS, which is the enhanced multi-broadcast capability that's an LTE to try to deliver some of these group call technologies, functionality. Release 13 is getting more work on proximity services and group call services. The mission critical push to talk has just kind of started. A couple of the people at vendors that I know and carriers that attend 3GPP, say a lot of this is going to get pushed even more into release 14. Okay, some future impacts. So in the next 5 years, we hope we'll start to see commercial deployment of some of these functionality services that I was just talking about. Hopefully we'll start to see some mission critical push to talk getting out there. It might not even be available until 2018, 2019. I don't think anyone has a real date for when the product availability for that will be. We talked a little about integrated operation of LTE and LMR is going to have to continue for the next 5 years. I don't think in the next 5 years anyone here would be giving up their LMR voice communications to go on LTE. Higher power, more ruggedized devices, obviously increase in LTE chipsets going into different types of sensors, devices, greater deployment of MIMO and carrier aggregation across multiple frequency band, greater use of heterogeneous networks, which we talked about, increased use of deployable mesh networks. There's a lot of talk about potentially taking the macro network because of there was the data surge that LTE dealt with the last couple of years. Now everyone's been talking about for a few years about the signaling surge. So there's some talk, I've talked to some European carriers that are looking at this, of making the macro network just for signaling and then the small cell underlying infill sites for traffic. Long-term 5G, the next 5 to 10 years, I'll give you a source. There's a couple things you can look at for this. It's going to revolve around, South Korea is saying that they think they're going to have 5G out in around 2020. That remains to be seen, but it's going to be focused around demand attentive networks. The ability of the network to be much more intelligent and being able to allocate capacity and resources where it's needed, when it's needed, based on who the user is, what the capacity is. Dynamic spectrum sharing, being able to use multiple frequency bands, not just one frequency band. How
much of 5G in terms of the basic elements like the air interface and things that are common with 4G, how much of that has actually been standardized at this point?
Oh, it's all a vision right now. I think, there's people starting to talk about it. There's a friend of mine that works for a carrier over in South Korea. They're having serious discussions about it in their internal meetings, but this is really a vision and kind of a concept. It's not something that I think anyone's willing to even start putting numbers behind and standards behind. It's really, it's pretty far out there. More convergence with wireless and fiber networks, so a lot of millimeter wave fiber, again, trying to get very small types of cells with very high capacity is going to need a lot more integration with wireless base stations and fiber networks. Okay, so LTE network design. So what I'm going to kind of do is go through some methodologies, information that you could use to develop coverage objectives, and then I'm going to go through some sample coverage centric designs for 3 counties in Colorado, as well as we took one county and tried to do a little bit of weighting of SINAR and tried to do a more capacity-focused design. But I'll talk about some of the assumptions in that when I get to it. So, I mean, we talked about this before, but what this is a plot of is this is the global composite total population density around Colorado. So anywhere you see blue, and it's obviously congregating a lot from Fort Collins down to Pueblo, going through Colorado Springs and Denver, where most of the population is. What this is a combination of the most current census grids where people statically live and work, but it's also been weighted and modified based on geotagged social data that's been collected the last 5 years from sites like Google+, Facebook, Twitter, to try to more accurately predict where users actually cluster and where they move during the day, ultimately where are they most likely to be in any 24-hour period, okay? Census data will tell you where people will be, potentially during the day where they work, at night where they live. When you put social data into it and you start modifying it, you really see, and this data has been collected over the last 5 years, and the more it's collected, the more samples you get, the more accurate it gets. It really shows where users are clustering and most likely to be.
So
yeah.
You're assuming that where the general population is going to be an analog to where public safety needs to be.
It'll help. It's not the end of the story, but it could be an outer bound. It will be one of the inputs as to when you start developing coverage objectives. And those coverage objectives could be developed in sections of the state, down to county level, city level. There may be different, throughputs that people want in different areas, urban versus rural. It's one of the input that you can use. It would be one GIS layer that you would put into an RF mapping tool to start creating a coverage objective. So this is the Centennial area where we are. I think we're right about here, 91, 95 east. So this is getting very down to, I believe this was plotted at around a couple of meters. But what's interesting, you can see the amount of people per square kilometer is most of it's washed out, and you're seeing 100 or 1,000 people per square kilometer. But you see here these dots, you're seeing where people are congregating. Don't know what's going on here, but there's a lot of people that are congregating in this area. Obviously, in these buildings, there's a lot of mobile users using data. This is just a 3D picture of it. I brought into to Google Earth. We're over here, right there. So you can the nice thing about this is it gives you kind of a heat map of where people are most likely to be, where loss of life could most likely be. Now, you might not necessarily use this for capacity planning, but you could use it as part of your coverage objective and coverage planning. I use this example. I was trying to find one in Colorado, and I couldn't find a good one because a lot of the temporary events seem to be in places like Steamboat Springs and where there was already population. But the Burning Man event's always really interesting. So if you go out to Nevada, in the desert in Nevada, and you look at the Burning Man event, you see all these people congregating, and this is all with social data. There's really no census data here at all, because if you look at the next slide, census data, it's all blank. There's nothing there. But you do see them when you look at the social data. So if you were going back to here and trying to encompass where everybody is, and of course we've got a lot of blue dots around here, and some of these lines are actually roads. People are scattered all over the place, but you don't have to remember where temporary events are if you start including geotag social data. You've got the whole quote-unquote population thing kind of covered as a coverage objective. And it's not perfect. There could be areas where people go where they aren't sending any social data or anything like this. I mean, again, you're relying on the sources of mobile social data for this. Another input is obviously going to be crime data. We looked at crime. I tried to find an area in Colorado where I could get critical infrastructure, EMS and police locations, and crime data all together. I couldn't find one in the time that I spent, but there's very good crime statistics that Denver City and County releases. You can download it. Jefferson County is kind of what a lot of counties do, is they kind of provide it on a map, but you've got to make a special request to download it, and then I request it, and then they think I'm, you know, some kind of a crackpot trying to get data. But, you know, if you're doing this planning for coverage objective for Colorado, you know, you would want to go talk to the PSAPs and the people that have 911 data, because you would want to collect that data and make sure that if, let's just say, for example, you said your coverage objective was everyone sitting in this area here, make sure all that CAD data is sitting in the areas that public safety goes to respond to 911 events is also sitting inside of there. Okay, so when we pulled the data, it was like a 60-some meg Excel spreadsheet, a CSV file. It was 336,556 crime incidents that were reported from January 2010 up to March 2015, so it's pretty up to date. Now, this is not just you know, murder. This is, you can see the legend. It's, you know, stealing, arson, aggravated assault, theft from a motor vehicle. This is plotting it all as points. And this is for the city of Denver and the county of Denver. Now, points are great, but what I usually like to do is I convert it to a crime density, so it tells me really where the crimes are more likely happening. And you can see in the red, it's really happening a lot in like downtown Denver is where you're really seeing, you know, which you would expect. It's a dense urban area. And if you look at Denver and you take this crime density heat map and you pull it into Google Earth, you know, the buildings obstructed a little bit. I kind of use this because it's a nice looking slide, but underneath those, but you have to remove the buildings to get, and zoom in here in the 2D version to see where all the red and yellow and green is. But it gives you a good idea of where crimes are occurring. Now, you might not have the time to go analyze every street corner in Denver of how much crime is occurring, but you just want to make sure that in general, this area of 911 responses is being included in your coverage objective, because you're going to provide coverage and some minimum throughput, but, you know, where are you going to provide it? Where do you need it? There's other data you can put in here. I didn't have a critical infrastructure slide, but I took this seismic hazard data from USGS, and I pulled it into the RF modeling tool I use, and you can see kind of in the upper northwest area, and more in the western area, you've got more of a chance of earthquake potential. So you could load this as a GIS layer as a coverage objective, map critical infrastructure and population over it, and you might have an idea if an earthquake happened, a forest fire, an avalanche, flooding, who would it look like it would mostly affect, and what critical infrastructure would it most likely affect. So this is kind of a, you know, ridiculous drawing, but it's a concept. It's trying to show you that, you know, you could have a global composite total population density, and this is greater than or equal to 5 people per square mile, as kind of a overall encompassing coverage objective. But you want to make sure your crime data is inside of that, and you want to make sure, if for whatever reason, I don't know how this would be possible, crime data would be sitting outside of that. You also could load in critical infrastructure here, geological hazards. But another thing I want to point out is up in the upper right there, that public safety area of operations. You know, what if there's a group of public safety that's going out and doing drug busts in the middle of nowhere because they know drug dealers are out there? Well, no one's making 911 calls to that area. No one probably lives there because they're trying to do it in secrecy. So this is the kind of data you would collect when you talk to your stakeholders and say, look, we know what the population is, we know where crime's occurring, we know critical infrastructure, we know geological hazards, but are there any missions you have where you need communications that could potentially fall outside of that? You know, draw a shape file in Google Earth or draw it on a map, and, you know, we'll import it into our GIS and RF modeling tool and make sure it's included in that overall coverage objective area. So, as I said, I couldn't pull all the data that I wanted to, but I just wanted to show you in the yellow, and this is kind of the Denver area, quote unquote. It's not just the county. You know, it goes beyond that. It's got some Jefferson County and some other adjacent Arapahoe. You've got crime overlaid with global composite population density. Now, you would want many more things, but this could give you a general idea if you got the stakeholders of the Denver area together and said, hey, this is what it looks like. This is what we look like where we need coverage. You know, what's your feedback on that? Are there any area of operations that we've got, you know, holes in here that we're missing? Obviously, this Air Force reservation, you know, there could be federal land that you might need to get input from federal stakeholders. And so it's just a concept. I'm not saying that this is the coverage objective that you would design towards. It's just, it could be part of one. I'm probably not going to go through this. This is a very, I'm RF engineers would argue with me all day over, you know, what's right and wrong here, but the point is what we're going to be talking about is if you see the link budget up in the upper left-hand corner there, when we do these RF sample designs, we're going to do a link budget, and a link budget's going to tell you, you know, what's your maximum allowable path loss, which is usually uplink limited. It's going to give you a link budget for one user sitting at the cell edge based on your minimum throughput criteria, downlink and uplink from a cell. What's the link budget for that? And you could do that in a spreadsheet. There's RF modeling tools that do that. You take what comes out of that, which is going to be what they call your reference signal received power, your RSRP, the minimum level of received power the UE can detect is like a beacon from the cell site to stay in a coverage area to meet a certain capacity throughput. And you're also going to take something from vendors, which is a link curve, which I'll talk about in a little bit, because you know what your minimum throughput need is. Maybe it's what I chose here. I'll tell you in a minute, but it could be 768 kilobits downlink, 256 kilobits uplink. That's the minimum guaranteed throughput you would give one user under the coverage of one sector, or what they call cell and LTE, but one sector of the cell site. And then you would put that into an RF modeling tool that would take all of that data and would start simulating a multi-network design, interference everywhere, and try to meet these SINAR values and RSRP values that you've given it that came out of your link budget and your vendor link curve, which I'll talk about in a minute. Certain input you would want to have to that is jurisdictional data, I'll talk about crime data, areas of operation, any assets that you want to include into that for asset site ranking. So you come up with your coverage objective area. You may want to prioritize use of certain sites based on their fact they're already hardened for public safety. They have very good fiber. They're good hub sites for line of sight for microwave. You load all that into this ACP, which is an automatic cell planning module, and it tries to figure out what are the absolute best sites to give you in that coverage area, meeting your capacity objectives, prioritizing any assets that you've put in there that you want to use first. In other words, you don't want to just create a blanket coverage area and say, give me the sites that I need. You want to try to use some sites that you have, and we'll show you some examples of that. Some reason it's kind of faded out, my arrows there, but I won't go into this too much, but this is a very generic, it's kind of a link budget process and developing what your minimum SINAR requirements would be. But you get general parameters, your operating band, 10 megahertz, what mode, we're doing LTE frequency division duplexing, you know, specifications of your devices, your channel, sorry, operating band 700 megahertz, your channel bandwidth 10 megahertz. You've got your OEM equipment specifications in the upper right. You know, what's the transmit power, your E node B, your antenna gain, your cable losses, noise figure, that sort of thing. You need this OEM link curve to derive your required SINAR, which I'll talk about in a little bit. What's your system overhead? I mean, you still have a lot of control channels, a lot of reference signals. You know, they can eat up 30% of the resources that you have. You need to know what that is. You put that all in, you'll get your maximum allowable path loss, which is usually, they're mutually exclusive. You've got your downlink from your E node B down to your device. You've got your uplink from your device up to your E node B, and it's one UE with one E node B. Usually it's going to be uplink limited because your base state, your E node B can transmit 43, 46 dBm. It can use 2x2 transmit diversity MIMO or spatial multiplexing MIMO. But your UE is 23 dBm, or if you have a power class 1, 30 dBm, it's much less power. So it's usually always going to be uplink limited. I mean, there are cases where you could be downlink limited, but that's usually the case. And what comes out is your target coverage. You want to use your RSRP threshold and your required SINAR, and that's what you really want to put into your RF design. If we get down in the weeds too much and nothing else makes sense, just remember your RSRP and your SINAR is what you're going to be looking for in your RF designs. Okay. So this is what I was talking about was a link curve. This comes from 3GPP. This is a very optimistic, some would say idealistic link curve. But the point of this that I want to get across is that once you know who your vendor is for your E node B equipment, and this is information that's guarded very much by the vendors. You know, they don't put this out for everyone to see. You need to look at what's your SINAR, and it says signal to noise ratio here because they're not really modeling interference because you need multiple multiple sites in a real-world environment to do that, but we'll treat that as SINAR later. What's the minimum SINAR you need? Because what people are going to tell you, they're not going to tell you, I need a SINAR. They're going to say, I need a minimum throughput. I need 3 meg down on my downlink at my cell edge. I need 256 downlink on my cell edge. Well, then you look at what's the modulation encoding scheme needed to deliver that throughput. And this throughput bits per seconds per hertz, you would multiply it by 10 megahertz for us. This is not a chart necessarily for 10 megahertz. This is just conceptually to show you what these link curves look like. You would need to know that the eNode B would say, okay, you have a certain application you want to do. You need a certain throughput. I need to know what the channel quality is that you have, which is based on SINAR when you do simulations, and then it ties that SINAR to a modulation encoding scheme, which ultimately tells you what your cell spectral efficiency or your throughput is, depending on whether you're including overhead or not. So this is the 3GPP link curve. It's not from a vendor. I don't have a vendor link curve, but this is just to illustrate what one looks like. Now, I talked about the RSRP, the reference signal received power. That's going to be your limit. That's usually something down like negative 113 dBm, negative 120 dBm. It could be negative 90 dBm if you're doing small cells. But that's basically, you can't go any further than that for the UE to be able to meet this uplink requirement, which I'm assuming it's 256 kilobits per second. And your SINAR is really for your minimum downlink throughput. So really think of SINAR as your downlink throughput requirement, and RSRP is your uplink. And the received signal, the reference signal received power is really almost like a beacon. It's the power of the reference signal from the base station. So what you would do here is you would take the results of your link budget, and then you would have all your sites. And what you would do is you would have you assume one person sitting at the cell edge in a sector, 100% load on that best server site. So you've got one user at the cell edge looking at an eNode B using 100% of those resources, and then you take all the neighbor eNode Bs and you assume they're 50% loaded. So their average utilization and traffic is 50%. And we're talking about traffic now, not control channels. Traffic channel will usually be your limiting scenario, not your control channels. So we're just talking about, as we're moving forward now, we're really talking about downlink SINAR, downlink throughput at the cell edge for one user. So what you would do is you would put all these sites together, and based on how the sites are, how the users are spaced, what the cell geometry is, what the average cell load is, which you're saying is 50%, except for when you're looking at your one guy sitting under his best server, and you try to extract what the actual SINAR is here. And this probability mass function is basically just discrete values, which could be area covered with this SINAR value. It could be population density covered, POPs covered with that SINAR value. But what you do is you calculate this in the RF modeling tool, and then what you do is you combine those results with the link curve that you got from the vendor, and this will tell you what your cell spectral efficiency is, or you can also show throughput based on a probability mass function, which again could be area that you're delivering this cell spectral efficiency or throughput, or the percentage of the population you're delivering it to. And your ultimate network capacity is really a function of the quantity of spectrum, which is finite, which is your 10 megahertz up and down, your cell spectral efficiency, how well did you place sites and design them, how much throughput are you getting out of it, and the number of cells. So if your spectrum's limited, your cell spectral efficiency is going to be what it is, and if you can't meet the network capacity you're looking for, then you're going to have to start adding cells. I know this is kind of getting a bit in the weeds, but I need to at least get some of these high-level concepts out of the way before we talk about the RF designs. Okay, this is just a design that was done in Central Park, which basically we were given a capacity demand map underneath. So we predicted SINAR, where it would be based on certain throughput levels and modulation encoding schemes, and then we extracted, based on where the population is, where should we place all of these sites to give the maximum SINAR to the population that's in that area. Okay, so I'll run through quickly some high-level RF design considerations for Colorado. Obviously, very dispersed population, very large area. 36%, I think that's a 2010, maybe it's changed a little bit, of the area is federal land. It's going to require a lot of infrastructure and type, number, and location of sites. You've got varying terrain, as you well know, the Rocky Mountains. I think that's Leadville that I have there. That's the second, I think, highest elevation in the 48 states. Out in the west, Rocky Mountains, you've got the Eastern Plains, and then you've also got, which are very flat, you've got out in the east, you've got the dense urban area in Denver. So real quickly, what we were talking about a little bit before, with the varying terrain, what you can have is that if you don't space your sites correctly and you don't use a very good resolution of terrain bin when you're doing your RF modeling, because of this varying terrain, you could get into here where you were talking about with your boomer site, right? So you've got a boomer site that's the best server to this site here, where it really should be the best server should be here, but because you didn't see this terrain when you were modeling, your modeling's not right. You're wondering why is the boomer site serving this guy instead of this smaller macro site, which is closer to it, which you get with varying terrain, because you get a lot of shadowing effects. And you would have to down tilt this guy over here to actually get to the design you wanted and maybe raise this guy up a bit. The other issue that happens, you see in the Eastern Plains, is that it's a very flat, so you could have too many, your best servers here, this is the one you want serving this guy as he's moving, but there's all this overlap from a bunch of adjacent cells, and what that does is that destroys your SINAR, because everyone else is interfering with you in LTE, because it's a frequency reuse of one. Everyone's using the same frequency. They're not separated out in frequency. And so what can happen is you get too much coverage, and you'll have to have these really ridiculously large handoff boundaries, which you can see here. And the longer you make that, but you've got to have a decent handoff boundary. It's got to be optimized, because if you're moving between all these sites and you're ping-ponging between all these sites, because in LTE there's no soft handoff and you don't have processing gain, and it's very sensitive to SINAR. What happens when you start doing stuff like VoLTE that's very latency sensitive, and your video, it starts clipping in and out because you're doing handoffs between all these sites. We really want to have maybe one or two, maybe three sites that you're looking at. And the longer you make, and the bigger this handoff region is, which is up here between these two sites, that makes your SINAR even lousier and lousier, because as you're traveling away from this site, away from the red site, you move into the blue site, your SINAR is tanking. I mean, you get a very poor SINAR, which means you get a very poor throughput. Okay, some other issues that weather and geographic hazards. Talked about that. That's obviously going to be it for hardening sites, and where to prioritize where you put sites needs to be considered. Okay, so this is not every parameter that went into the link budget that we developed. We did. Kim sent us Jefferson County, which is kind of a urban to suburban, moving into a rural county, just west of Denver, actually very close to Denver. We did San Miguel County, which is one that's very mountainous out in the west. And then we were given Yuma County, which is a very flat county out in the Eastern Plains. So we saw all of these different type of RF effects. But just real quickly, this green box here where I say OEM specified, I don't have an OEM link curve. So what I did is I made up my own link curve. I did link budgets. I used a link budget tool to look at throughput and various different SINAR values at different, RSRP and predicted SINAR values at different throughputs to build my own link curve. So what I came up with, which was my criteria, was I said, let's assume that we're doing a lot of video. So if we can look at the cell edge user throughput first, I'm assuming at the edge of the cell, every single cell that we plan, you'll have 3 to maybe 4 simultaneous video users. So I need 3 meg at the cell edge per sector on my downlink. My uplink, I just chose 256 kilobits. You may have scenarios where you need to flip this, where you need 1 meg up and 256 down because you're broadcasting video from the edge of the network. But the design we did, we assumed a high throughput on the downlink, low throughput on the uplink. So basically at 3 megabits, the lowest SINAR I want to see is -1 dB. So on that link curve, if you can think of the link curve I did, at -1 dB SINAR, that ties to a modulation encoding scheme that's going to give me 3 meg at the cell edge. And the RSRP, when I did the link budget, was -113 dBm. Now, it's uplink limited, so beyond -113 dBm, if my UE goes beyond the point where I see this RSRP at -113 dBm, so I see -115 -20, eventually I lose connection with the network. I can't guarantee 256K on the uplink anymore. A couple other parameters, obviously we're in the 700 megahertz band, 10 by 10 bandwidth, it's data. I didn't do any voice or anything, it's just a data service. Cyclic prefix is normal. If you're interested, I can get into that later. MIMO, I'm assuming 2 by 2 at the transmitter, but really 1 by 2 on the UE. So the UE really can't take advantage of really good spatial multiplexing, but I'm giving it transmit diversity at the edge of the cell. The power amplifier E node B transmit power is 43 dBm. We did have a couple of antenna. We did have a couple heights in the database we were given, but it was missing. So a lot of sites. So we just said we make everything 24 meters. So please keep that in mind. The antenna center line of every single site is 24 meters. You won't see that in the real world, but we set everything to 24 meters. UE power class is 23 dBm. What else I want to say? Cell loading. We assumed when we did the analysis, in other words, every cell but the one from the one user's point of view, looking at the best server who's using 100% of the resources at the cell edge, which gives them 3 megabits throughput, we're assuming every other cell is loaded at 50%. You start loading cells around at much higher cell loading, you go to 80%, your SINAR is going to get affected by that, the cell edge. Okay, and cell area availability, we shot for about 95%. I mean, so we were trying to make sure that there's a 95% probability that if you're in the area of coverage, you've got a 95% probability of setting up a data bear and at least getting 3 meg down and 256K up. Okay, real quickly, the antenna that we chose, this red pattern is the horizontal beam width. The blue is the vertical. So if you can think of a balloon, if I take a balloon and I start pushing it together like this, I don't have as much beam width horizontally, but I start pushing it, but then it gets much better vertically. So one thing I want to mention, this is a very, it's a 95-degree beam width antenna, and it's 11.7 gain. So it's a very wide horizontal because I'm pushing a coverage-centric design is what I'm really doing. So because in the vertical shape, it's not so good underneath the cell site, you won't see a lot of extremely high data rates close to the cell site. We're trying to get at least that 3 meg guaranteed to one user in a time transmission interval. So we're really pushing the capacity out. It's dominant away from the site. If you change the antenna, you get a tighter horizontal beam width and a better vertical, then you might not get as much coverage of that 3 meg out, but you'll have more dominance closer to the cell. Okay, first county up is Jefferson County. This is kind of the urban to suburban rural. We had 500 sites. We used 371 in the analysis that were located in Jefferson County. Again, we are not taking the county and saying, I'm going to go pick the absolute best sites I can. We're being anchored by the sites that we were given. So of those 371, looking at the SINAR distribution, we selected 27 of them so that everywhere in here you see this coverage going down to -1 dB, because remember that's my cutoff criteria tied to my 3 meg downlink. You will get a SINAR of -1 dB or better in this area. Okay, and well, I'll get to what we covered a little bit later. Now, this PMF, this probability, it's a little confusing. The probability mass function, I'm basically taking the SINAR and I'm bucketing it in values. So the SINAR is the -1 going up to 20. Now this unweighted PMF going up to the on the y-axis there, those percentages, that's area covered. So if you look at it and you say the SINAR of 1 dB, about 3% of the geographic area that we covered is going to see a SINAR of 1 dB. So what we look at in a cumulative distribution function, we look at it and we say, well, where do we cross the 50%? Well, we cross it around 8 dB. So we're saying in this coverage area here, 50% of the area under this SINAR will see a SINAR of 8 dB or better, or 8 dB or worse. So what you would do is you would extract this SINAR value of 8 dB, which it's a median, not an average, because it's not a Gaussian distribution, so it's a median, and you would go back to your link curve and say, oh, at 8 dB SINAR, what's my modulation encoding scheme, and what throughput do I get? So what can I kind of expect is my average throughput for one person per sector moving around in this sector. So if you had one person here, starting here, you know, their SINAR would be up around let's say 17, 18 dB, if that person starts moving, their SINAR starts degrading, which means their throughput starts degrading out down to here to like -1, okay? This doesn't mean you can throw 100 people in this sector and they're all going to get 3 megabits. It's one person at the cell edge at -1 dB SINAR gets 3 megabit download, and you're utilizing all the resources in this sector 100%. There's no resources for another. You're using all the resource blocks that are available. If I took more bins and I had more values between -1 and 20, we could start changing this to a probability distribution function, and it would be more like real values instead of discrete values. So we're showing we've met our SINAR criteria, and we're using 5-meter resolution terrain bins, by the way. The tool goes down to 10 centimeters, but I think for the purposes of this, 5 meters is quite good. Same 27 sites. Here they're satisfying SINAR. So the dark blue, you're seeing the -113. So if the UE is sitting here, based on our prediction, it should be able to do at least 256K kilobits. One person in this sector here, one person. Another person, another sector could be doing it again, but you can't have any more people. Now this is frozen in a time transmission interval of 1 millisecond. So this is a snapshot of what's happening in every time transmission interval, which LTE works off of 1 millisecond, okay? The next millisecond, something different. So it's one user in that time transmission interval getting, as long as they're here, they get at least 256K. As they start moving up, they could go up and get megabits of uplink. But we're trying to say, show us the sites where that minimum criteria of 3 meg down and 256K up. So now I'm a little nervous about showing this because I show this. This is me. I did 13 steps in my OEM curve that I built based on reasonable values, talking to my friends in industry. So I did 13 of them. I'm only showing 11. I have one for 2 megabit and 1 megabit, but I'm only showing 11. So I'm showing 3 meg to 33 meg. And what I'm doing is I'm saying, okay, when I was showing you the SINAR plot before, I'm showing you area. What's the area covered with the SINAR? Now I'm using global population density, and I'm saying, okay, let me pull new statistics. The SINAR is the same, but now I'm saying instead of % of area covered, what's the % of the POPs covered? And you can see that in the area we had, what, 8? So we had better SINAR because in the area we're assuming uniform distribution of users. We're not assuming users are congregated anywhere. Once we start doing that, we see when we weight this SINAR based on POPs, it goes to 7.5 dB. So what that's saying is that if we look at the 50% and we go over the cumulative distribution function, we say about 50% of the people in this coverage area, not including this area here, but in the coverage area, are going to experience the SINAR 7.5 dB or better, or 50% are going to experience 7.5 dB or worse. But again, this throughput, this is based on a link curve I created. It's not based on a vendor link curve. You would need an actual vendor link curve to take this SINAR distribution and tie it to actual throughput through modulation encoding scheme values. Okay, this is just a zoom in of, just to show you this is near Golden. Here's a zoom in of the site between Wheat Ridge and Lakewood near Crown Hill Lake, just to show you kind of what the throughput is. Again, I'm not telling you if you go take my link budget and this tool and you go put a site there, that when you're sitting right here, you're going to get 12 megabits on the downlink. This is my OEM. It's a reasonable value. You wouldn't see something drastically different from that. But this is my link curve I'm using, okay? So I want to make that clear. And another thing I want to make clear, which I should have said earlier, you can have users in here, and if you pull statistics from the switch, there will be users that will still be able to connect to the network at below -113, right? They'll be able to connect to the network down to what their UE can handle, their receiver sensitivity. So you may see statistics that won't match the statistics I'm showing, but I'm only talking about in this coverage area with this criteria met. So there's a difference between the coverage statistics I'm showing you and performance statistics you might see in the actual real network, because you could still have people attaching to the network at less than -113 dBm and getting throughputs on the downlink less than 3 meg. Okay, so Jefferson County, we said, okay, well, let's assume here that 27 sites, so we would take 27 sites multiplied by whatever throughput 7.5 dB SINAR equals, based on our link curve, multiplied by 3,600, and that's the total bits we're giving in this area in the busy hour, right? And say that's good for public safety. But say public safety does an agreement with a spectrum sharing partner, and the spectrum sharing partner says, I want like 3 or 4 times that across that area. So what do? We've got our cell spectral efficiency done. We've got our bandwidth is 10 megahertz. The only thing left to do is start adding sites. This is just showing you the global population density around Jefferson County. So what we did is we said, okay, let's assume that someone came to us and said, you've got total capacity in 90% of the geographic area of Jefferson County. You're giving us 27 times whatever that throughput is at that median SINAR we calculated, plus 3,600. Well, we don't want 27 times that. We want 96 times that, or we want some number of capacity that this network can deliver over that area. So what we said is, well, what happens if we use 96 sites? Okay, we've got more sites, so we've increased the overall network capacity. But you'll notice this weighted value, 27 sites, is 7.5. Now what happens when we do 96 sites? Now it's 5.6. Well, why? Why did the SINAR go down? Why is the average throughput going less now? Because the median SINAR has gone down. Well, the problem is we've jammed more sites into generally the same area, so now we've got much more interference, and we've kept all those antenna center lines at 24 meters, right? We haven't optimized anything. So I wanted to do this to show you that we get a little bit more coverage here. We increased the coverage a little bit. We've added a lot more total network capacity, but we've tanked our SINAR. So what we would do now in the real world is we would start looking at changing antenna center lines. We would look at a library of antenna types, maybe change antenna types, down tilts, both physical and electrical, and see if we could optimize this to get it back to a SINAR, a median SINAR of 7.5. Is this like kind of clear? Is it in general, or the concepts clear? And then I know I'm getting down the weeds. One more thing, with these 96 sites, I also wanted to show, okay, where are we not satisfying SINAR and RSRP? Which, you know, a lot of people maybe selling you equipment might not show you something like this. They'll show you this and say, look at that, isn't that great? You're gold. As long as you don't go down here in the middle of nowhere, you're fine. Well, obviously at that level of plot, you'll see in the black areas, we do still have some areas where we're not meeting our RSRP and SINAR requirement. Now, can someone attach to the network there and still do something? Yeah, probably, but they're not meeting our minimum throughput criteria of 3 meg down to 56K up, tied to those SINAR and RSRP values, which, you know, you would be doing when you get throughput requirements from stakeholders. Okay, so San Miguel County's down here, very mountainous area. Telluride, I guess that's like a ski resort pretty much, right? So a lot of tourists in there. The sites, we had 84 sites we were given, but you notice they fall into 5 tight clusters, except for a couple of out there sites. So we know we're not going to be using all these sites. We're going to get lots of interference, especially in Telluride, because it kind of goes down in the mountain. And if you start putting a bunch of sites, they just blow each other off the air. So let me notes I had there. Okay. All right. Let's read it. So what we did is we said, okay, with 6 sites, you know, we're meeting our SINAR of -1 and our RSRP threshold of -113. And if you remember where the sites were, you know, we're kind of on top of those sites here. And if you look where the global population density is, with those 6 sites, we're doing a pretty good job of covering where most people are. But if you can see, it's kind of hard to see, you'll see these red areas here. Well, what is this? This is people going around on the roads there. So there's still people that, you know, could potentially get hurt. I don't know in that area if they're, you know, biking during the summer or whatever. I think Colorado's got a lot of outdoor activities, right? So there's people that could get hurt and need rescue. And it really shows here when you look in Telluride. What I love about the social data is you can see the people going up here. I mean, it's amazing. And this is not a road that I drew here. This is, you see the road because you see all the social data stuff that's happening on that road. So there's definitely, you know, out in these red areas here, you know, there's still people out there doing things. It's not just the population centers. We ran it again at 11 sites, but I don't think the slide really shows a whole lot interesting. So now we're going to say, okay, in Jefferson County, we added new sites for capacity. Now we're going to say, in San Miguel, with these 6 sites, we covered, when I ran the statistics, we covered 48% of the geographic area with at least 3 meg or better. So that's like half the area, you know, not so great. So what we said is, how many more sites would we need to try to get that coverage objective up higher? We're not given any more overall, we're not really going for capacity, we're just really going for coverage here. So the good thing about this tool that I like is, one thing it does is it doesn't let you go put sites in the middle of nowhere that you can't access and you can't backhaul and you can't do anything with. So I cut a lot of its criteria out, but I got it back to the point and said, look, only give me candidate sites that are within 20 meters of some road. Don't give me something that's 100 meters away from the road. So I just wanted to point that out. So what we did is we said, okay, to get up to 90% geographic coverage, we're going to add more sites. So we went from 6 sites up to 21. We added 15 new sites. Now, I do apologize. When I ran the terrain bin resolution, I didn't run it at 5 meters. So it's a little bit coarse. But, you know, I would rerun this again at a 5-meter terrain bin. But the general results are still the same. And there's certain criteria. You say, you know, we want sites 10 kilometers apart, or it's got to cover at least 10. You want to have some filter to say, we're not just going to put a site to cover, you know, half a kilometer. You want to have some criteria, some area of coverage. Otherwise, it's not really economically, even for coverage, to build a site. Yeah.
Can you run those with prominence in low dense population?
Yeah. Yeah. Actually, it's funny you said that. We actually had I wanted to simplify things, so I specified one type of antenna. I said make everything 3D sector, but you're absolutely right. When you get out in these rural areas, you don't need the capacity coverage. Why not use an omni antenna? Why use a 3-sector site? Absolutely. So this shows where your SINAR and RSRP threshold aren't satisfied. Now I want to say one quick thing. The tool does an analysis over this rectangle. So you'll see the statistics coming out of it, but when you run the statistics, it's run based on the county as the analysis target. So I'm not giving you statistics for out here. You are getting them for the actual county. Yuma County, okay, that's in the Eastern Plains. We had 54 sites congested together. What we ended up doing to meet our criteria, unbelievably, and I can't remember how many square kilometers it is, it's pretty big, 6 sites does it, simply because it's so flat. Again, at 24 meters. I mean, if you couldn't mount that high, you could maybe use less sites if you had higher antenna center lines as well, because it's simply just so flat here. Now, well, I'll get to that at the end.
2,300 square miles.
Yeah, it was 2305, was it?
2369.
Oh, okay, yeah, what was it, 3305? I can't remember San Miguel or Jefferson. Yeah, I said, yeah. So that's a lot of geography. It's 98%. Okay, some quick things to remember. The locations of assets haven't been verified for positional accuracy, so we haven't gone out and surveyed them. You know, coordinates could be off a little bit. They always are in any database. Some of them might not be suitable for development. You can't put antennas on them. You know, the wind loading might not have the right backhaul. Some of the sites in the county were not modeled due to close proximity. You know, 763 megahertz with, you know, sites at 24 meters, which maybe aren't high antenna center lines for public safety, but they're pretty good in the commercial. I mean, you get a lot of interference. So we wanted to maximize SINAR. In fact, an important part here is the SINAR, which I wish I would have plotted it, is great here because you just don't have a lot of overlap. And this would be a really clean design. High sites could use to provide more coverage. The traffic modeling is different without a traffic. So the SINAR distribution is the SINAR distribution, but you can pull and weight the SINAR you show people based on an underlying traffic map, so I did it for the global population density because I didn't have anything else, but you could do it with crime data. You could weight it in different ways. You could say, I want to see a SINAR distribution. Where's my last one? 85. I want to see a SINAR distribution like that. I don't care about POPs covered and area coverage. Show me how much of the hot crime, show me areas where 100 crimes or more per mile every 5 years is getting covered. So you can do anything you want. You can, as long as you have it in that GIS layer and you have that data, you can weight the SINAR and pull the statistics any way you want. The SINAR isn't changing. It's just I'm pulling the statistics and showing you different median SINAR based on different weighting. Area, pop density covered, you know, you can do it crime. You could do infrastructure. I mean, there's a lot of different ways you can do it. So this isn't the end of the story. Let's see, okay, things to remember. Adding sites, you can increase capacity, but as we saw, we went from a SINAR of 7.9 to 5 point something. And actually, when I ran Jefferson again at 220 sites just to see what happened, the median SINAR went to 3. I mean, it just starts tanking because you just get all sorts of interference. Okay. Well, what I didn't use here is we can get very accurate with the terrain bins. We can do 1 meter, you can go down to 10 centimeters, and it will calculate all the different modulation schemes in every single one of those terrain bins. We didn't use 3D building data. That's kind of a premium service. 3D building data will help you determine a lot more shadowing effects. The point here is that a lot of propagation tools are empirical. They're used like COST 231, Okamura, HADA. They use empirical measurements and interpolate to different frequencies. Some are more valid in frequency bands than others. When you start getting very accurate building data, vegetation data, very tight terrain bins, your models can start becoming almost deterministic. Because RF engineers put these fudge factors in for like log normal fading, gain against shadowing, all of that, and they'll put in some fudge for a couple of dB depending on the morphology they're in. If you can get very highly accurate data, you can start almost getting a deterministic design. And I've done designs on other projects with this tool where we've done these plots and we've pulled metrics from one of the carriers, their vendor equipment, and it was unbelievable how close our predictions were. I mean, RSRP values within like a dB or so. I mean, it was stuff that, you know, with all the great data that's out there now, what you can do with it, the RF designs have gotten so much better and so much more accurate. Okay, so one real important point is to say, I kept everything at 24 meters. This is not an optimized design. So this is not, these designs are not go build with this. You have to optimize them. You have to change down tilts, antenna center lines. You need better traffic map data to where do you really need the coverage and where is its part. If I really figure out what for your specific case is the median, is the throughput you're looking for in a certain area. So what is that median SINAR, that median weighted SINAR that you want? It might not be POPs, it might not be crime data, it might not be area covered. Changing the antenna. So you could do an optimization where you could change and use different antennas at different sites depending on where they are. And in rural areas, you know, wide beam's great. If you're in areas with terrain, you want a tighter vertical beam closer to your site, and you're trying to shoot down a canyon or a canyon of buildings, different antennas. Now, you can't go use hundreds of different types of antennas or you go broke because you need volume discounts, right? So usually you go in a market and you choose a couple different types of antennas with MIMO, but you could do that. So it's like I said that. So yeah, the design's not optimized. So I don't want you to think that. And you need the use of a true OEM link curve. And the RF engineers that do the work, that have an NDA signed with the vendor, whatever, they need those values. Again, it's not a, you know, I'm not saying this is X vendor's performance because I don't have their link criteria. The other thing too is that a lot of how the packet schedule, these things called downlink and uplink schedulers, these are the things in the eNode Bs that build resources and resource blocks and frequency and time based on what application you're using, who you are. All that's very secret sauce. So when I did this link budget, you know, I assumed like a fair proportional scheduler. You know, that might not be the algorithm that a vendor would use. Also, in all of these, this is outdoor. I'm not necessarily guaranteeing any in-building penetration. You do get good penetration at 700 megahertz, assuming the buildings aren't made of that material, that are ecological, that, you know, block 700 megahertz. And I used a channel model of pedestrian. So, you know, this would, so it's a very important point, I should have made it earlier. This is someone walking around what they would get. If you start getting in a vehicle and you have a bigger Doppler shift of 70 hertz, this would tighten up a bit because high mobility starts to affect SINAR more. And certainly, this would not be the coverage if you had a bullet train going through here. It wouldn't look anything like this. So, yeah. Well, the thing is, I've got I've got a friend in Japan. They're testing these, you know, 300 hertz Doppler effect because they've got these high-speed trains going through dense urban areas that, you know, we don't really. I never really think to design for. So. Yeah, but Yuma County, this is probably pretty good. I mean, if
don't worry about your silo coverage.
Right. Yeah, that's it. Okay, that's kind of it. There's a lot behind this and assumptions I made in the link budget and the modeling that I didn't go into, but I just wanted to get those high-level concepts clear. I think if there's any backup stuff that,
What
okay.
about multipath? That's a big deal out here.
Yeah. So when you mean, yeah, so this is where we saw a lot of multipath based on terrain, and here is where we saw a lot of multipath based on buildings up in here. This area up in here, as you start getting into Denver, you start to see you're getting a lot of multipath and diffraction because the buildings are starting to really take effect, and that's why the coverage areas of the sites are shrinking.
But here mountains too.
Yeah. I mean, so the clutter that was used for this is pretty accurate. So it's taken into account all that multipath fading, and I made the assumption that you could use transmit diversity at the cell edge for like a 3 dB boost with MIMO, with 2x2 MIMO at the base station and 1x2 two receive antennas on the UE, but not doing MIMO on the uplink. But when you mean multipath, was there like a
The Granite Mountains found in the first digital systems out here.
Yeah.
It was a nightmare. It
Yeah.
was kind of what was discovered.
Yeah.
And, you know, I just wondered where you were at with that. Seemed like a good
Yeah.
thing to throw out there.
Yeah, so, you know, the only one we really saw with a lot of, you know, terrain.
How does this account for that? Does it?
Yeah. So it accounts for a shadow. So the best way I found, so usually when you do, like you do say cost 231 or Okamura-Hata model, you know, you say, well, I've got log normal fading or shadowing. I'm going to assume, you know, this dB for urban, this dB for rural, this for whatever clutter type. The thing that's very good about this tool is the terrain data is so precise, down to 5 meters or less, that if you look at the Bernardine-Menage rule, where you basically say, you know, the cell range, the radius, and you start dividing it by 40, and that's kind of the terrain bin you want to look at, but then you could divide it by 28, because that's all the modulation and coding schemes that LTE offers, right? So you're kind of taking like a cell range, dividing it by 40, and then dividing it by 28, and I don't have my laptop up, but one of the cell ranges in the suburban area, I think, was like 5.6 kilometers or something like that. And when you start dividing that, you start getting down to, okay, yeah, 5 meters. I need at least 5 meters to avoid any quantization error and make sure I've got all the multipath and all the diffraction and everything accounted for. So I can't say that with this design, you know, how accurate this would be in terms of, you know, the SINAR would be off half a dB or the RSRP would be off a dB, but this tool typically for me, and again, I can't endorse anything, but very accurately models all that shadowing and terrain very well. And the more accurate data you have in clutter, you know, the more deterministic your modeling becomes and less empirical, and you can start reducing that that fudge factor you've used for like the shadowing and log normal staging. There was one thing I wanted to, one more point. It's kind of this is, yeah, so here's Jefferson County with all the modulation coding schemes.
Looks like art.
Yeah, it's, let's see, I wanted to show this. So there's a thing in interference margin, which 3GPP has a formula for it. And maybe it's a little confusing to show this, but one thing I wanted to mention is that we designed everything so if you look here at 1, let's say this is 1. So this is the SINAR that was required by our link curve, and what we actually designed was 1-to-1. We did a great job. Our SINAR is 1-to-1 actual with what was required. But we went down here and we did it assuming all the neighbor cells were at 50% load, right? So we're looking at an interference phase margin of maybe 2 to 3 dB, okay? Now with public safety, you know, one of the key things when you're talking to the stakeholders is, you know, where do you anticipate major events occurring? Where could we see cell loading of like 80, 90%? Now this graph is a 3GPP formula for interference phase margin. So I'm not saying that all these numbers are exactly right and what you'll see in the real world, but it makes a good point, and one of my friends plotted this, is that if you start at neighbor cell 50%, you've got a 2 to 3 dB fade margin, not fade margin, interference margin. If you start loading your neighbor cells up way high, look at the interference fade margin you're starting to see. So what does that mean? Well, when I did the link budget, again, this was uplink limited, right? So I think my maximum allowable path loss on the uplink was about 140 something dB. On the downlink, it was 150 something. I think there was like an 8 dB difference. So what happens to the guy who's sitting at that cell using 100% of those resources at 3 meg, and all these neighbor cells start exploding? You know, we're assuming he's got a buffer of somewhere here. Well, now he could be up at 11 and 12. Well, he's still got some fudge factor to eat away at, because our link budget on the downlink had 6 to 8 dB more than what we counted for on the uplink, because it's uplink limited, right? But when you start eating into that, then you get to the point where your downlink maximum allowable path loss and uplink maximum allowable path loss start to equalize, and then it gets worse. You're not going to see that 3 meg at the cell edge anymore, because again, we assume all the neighbor cells at 50%. So I want to make that clear that, you know, when you're designing a public safety network, everybody assumes this baseline of 50% of the neighbor cells, but what if you got cells going 80, 90%? Well, the person in that adjacent cell that was getting 3 meg, if it gets bad enough and you start getting up over 90, you just kill that fudge factor between your downlink, and you're not going to get 3 meg anymore. You'll get something less, and if you want to get 3 meg, you have to move closer to the sites. I wanted to make that point because, again, there's a lot of assumptions being made here, and I just want to make sure they're clear. Is there any questions? How are we doing on time? Are we,
We're about 10 after.
Oh, okay, so we're done, unless anyone has any, sorry about that. Yeah.
One other thing I'm sitting close to. All of that said, when you're doing your original design, why wouldn't you start with corridors like 70 and 25 versus existing sites? Because these corridors, you know, are your highest population density, most
But it doesn't
valuable
mean
assets.
it's your highest
things like
public
that.
safety action.
Yeah. So weighting it on population,
They
yeah.
are, you know, the most valuable assets.
Well, it
I
depends.
think
See,
you have lots of people in this room
Yeah,
who would argue differently.
Well, no, infrastructure, things like that. I mean, the most expensive buildings, power plants, refineries, things like that, they're all pretty much focused on either 70 or 25. A lot of them. I mean, the vast majority. So instead of starting a design with existing towers, why wouldn't you look at our big corridors first and then build out from that? I'm just wondering if.
well, so in
I'm throwing it out.
yeah, we didn't consider priority of build in this. Obviously, we just said, hey, cover the sites, use these sites we were given as anchor sites, and then if you need to add sites, you can add candidate sites. But you know, in any wireless build, right, you always start a commercial wireless build. You start with the cities and the roads connecting them.
No, you start with the corridors.
Well, I don't know. Me too. So, but the thing here is that if you've got an existing LTE commercial infrastructure, right? So it's going to be quicker. And I know rural people, you know, and it's going to be quicker to put equipment in those urban areas because there's infrastructure there. It's going to take longer when you've got to build, because you go outside the commercial areas outside here and you start getting out here, there may be some LMR assets that you can use, but they're not going to cover everything. You're going to need new sites. So you're going to have to build greenfield sites, and it's going to take time to do those. There's zoning, construction costs, there could be legal issues. I mean, who knows? So yeah, I mean, it's quickest to build out this, fastest to hit the most pops if that's what you're looking for, right? And okay, we could maybe the corridors first, okay? Build out all the highways first.
Just a question.
Yeah, it's you know, what's the priority? I was in the Oregon consultation, and you know, the rural guy got really upset because I said something like that. I was like, okay, I didn't mean that. But any other questions? Or okay, well, I hope this was of value. Thanks for coming and sharing your time with us.